All right. So today we're going to introduce the idea of limits, although I think you've already seen them in Algebra 2, right?
No.
Yes? Okay. I'm pretty sure Mr. Thompson talked about them some. Yes?
I don't really know about much.
Yes? No? 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 Maybe? Mr. Walker? No? Okay. That's fine. I mean, it's not an Algebra 2 topic, but I just know that they did a very good job of covering the Algebra 2 material, so I wasn't sure if they covered this too. Anywho. Okay. Okay. Yep. So, and we're going to be staying in this. We're going to stay in this concept for a few days. Okay. So we're going to introduce them today. We'll do a little bit more on Monday. I think a little bit more even on Tuesday, kind of thing. Because this is, really like we're on the borders of calculus now with this. Okay, we're just like kind of pushing in just a little bit. This is an actual unit in calculus too, so as well. Okay, it's in calculus 1, but anyway. So we'll just kind of dive in here with an example. So consider g of x, which is equal to 2x squared minus 5x plus 3. We'll put that all over x minus 1. Okay, right? This is the exact function that we just talked about in the warm-up. All right, so I wanted to introduce it there so that way it would be more familiar here. Okay. We saw in the warm-up that this simplifies to be 2x minus 3 as long as, x is not equal to 1. Okay. So in other words, right, if we wanted to graph this thing, and I showed you the graph on the graphing calculator, but we'll sketch a graph right here. Okay. The graph of this nasty-looking rational function ends up really just being the graph of 2x minus 3. And what is 2x minus 3? It's a line. It's a linear equation. Slope is 2. Y-intercept is negative 3. So let's just go ahead and 1, 2, 3. So there's my y-intercept. 1, 2, 3. Like that. Okay. So slope. The y-intercept is negative 3, so I put a point there at negative 3. And then I'm going to use my slope. So up 1, 2, right 1. But then at this point, right, I'm going to put an open circle. Okay? Because x can't equal 1 right there, right? We're kind of have this open circle. Then I'll go up 1, 2, right 1. And so then there's another point, and I'll just go ahead and just connect these dots and draw a line there. Okay, like so. Now, the graphing calculator doesn't do a very good job of showing the hole, depicting the hole in the graph, okay? And that's because of the way the graphing calculator graphs things, right? It kind of has to decide, the graphing calculator makes pictures by deciding whether to turn on or off those pixels on the screen, right? And so if there's more graph than not in that pixel, the pixel gets turned on, okay? So in this case, right, there's only one single point where the graph doesn't exist, and all the other points in that little pixel would still exist, so it goes ahead and graphs it. So you don't really get to see the hole on the graph, okay? But we're going to show it here because it's important for us to understand it, okay? And of course, we already know, we already have an idea here, right? I mean, at 1, we know that there's a hole there, but it's like, man, what happens though as x approaches 1, right? So we don't want to just be satisfied with saying nothing happens at 1. Maybe we can talk about 1 by saying what happens as x approaches 1. Okay. And this is where we introduce the idea of a limit, right? We are going to approach a value. We're not going to actually be at it, but we're going to approach it. Okay. Or the idea is we're going to get closer and closer and closer. All right. So let's do that. Oh, I should know g of x. Let me call it that. Okay. So let's perform this idea of approaching 1. So let's pick something that's kind of close to 1. So I'll pick something, kind of simple like 0, for example. 0, it's kind of close to 1. We'll start there. If I plug in 0, what do we end up with for our function? What is g of 0? It's going to be negative 3, right? It's got to be negative 3. Just plug 0 in, right? 0 minus 0 plus 3 is 3. Over 0 minus 1 is negative 1. 3 over negative 1 is negative 3. Okay? Let's get even closer to 1. Let's say something like, I'll get closer this time. I'll say like 0.9. Okay? And so now it's like, this is a little bit more work than we want to do, so I'll go ahead and just do that in my calculator here. I get negative 1.2 if you plug that into your function there. Okay. So that's like pretty close, but let's get even closer still. Let's try like 0.999. Right, see what happens there. So if I do 0.999, I'm going to end up with negative 1.002. By the way, let me just do a little sidebar here real quick. I don't know if you knew this or not, but I'm going to tell you about it. Okay, so with your graphing calculators, right, if you're going to be doing, and maybe I've done this before with you guys, forgive me if I have, and just endure it for a few more minutes here, but if you're ever going to do repeated calculations with the same function, right, if you're going to keep plugging in like different x values for the same function over and over again, it can be helpful if you press the y equals button and you type your function into y1. So I type my function, there's my numerator in parentheses, there's my denominator in parentheses, right? We're dividing there. Okay. If you type that into y1, and if you press second graph, right, it takes you to your table. But my table is a little bit different than your table might be, and that's because normally your table looks like that. Okay. The table is automatically filled in for you by the calculator, right? And that's all determined by your table setup, which is arrived at by doing second window. Okay. But you can change things. So, for example, you can change where your table starts by just changing this number here. You can start at any number you want, and you can also change how the table changes. Right? This is supposed to be delta table. The Greek letter delta, right, is used to represent change in math and science and stuff like that. So this is starting at 0. It's going to go up by ones. But here's what I like to do. I like to change my independent variable, my x's. Instead of having the calculator automatically fill it in, if you arrow over and hit enter, it will now wait for you. The calculator will ask you what to type in. So now if I press second table, it's waiting for me to say a value. So I can say, let's see, what's the value of the function at x equals 2? And I hit enter, and then boom, there's the y value. Okay? Or at 3, and then boom, there's the matching y value and stuff like that. So it's helpful for these like repeated calculations. So continuing on with our table here, right? If I say, well, what's the value at x equals 1, right? If I type in 1, we get an error because we know there's a hole there, right? There's no value. It's indeterminate form. So let's try now. So we kind of approached 1 from the left-hand side, right? From values less than 1. Let's now try and approach 1 from the right-hand side. So that means we would be like 1.001 would be kind of like the complement to that 0.999 there. So if I do that, 1.001, we get negative 0.998. Okay, and then I'll do like 1.01, moving like further away now from the 1, and we get negative 0.98. And then I'll do like negative 2. Well, not negative 2, sorry, I'll do positive 2. And then when I do positive 2, I get 1. Okay, and so the question is then, right, it certainly seems like as we approach 1 from the left, as we approach 1 from the right, as our x values approach 1 from the left and approach 1 from the right, our y values, our function values, also approach a value as well. And what is that value? It looks like it approaches negative 1 there, right? This is getting closer and closer to negative 1 from the left-hand side. This is getting closer and closer to negative 1 from the right-hand side. And so it looks like we're approaching negative 1. Okay? So questions on any of that so far? That's the idea of a limit right there in a very basic sense. Okay, so we can say here, g of 1 is indeterminate. Okay. But as x approaches 1, g of x moves arbitrarily close to the value of negative 1. Okay. So what do I mean by arbitrarily close? Well, the idea about arbitrarily close, right, well, is really the idea of close. What does close mean, right? Close is just like by comparison. And so some people might say, oh, Mr. Witt, I'm not going to believe this thing gets to -1, because technically, right, we're still not at -1 here, and technically we're still not at -1, right? Both of these are off by 2 thousandths, okay, from that -1. So you might say, Mr. Witt, I'm not going to believe that it gets close to -1 until you're within 1/1,000,000th or 1/1,000,000,000th or something like that, right? So the idea here, though, is that we could show that. We could, if I wanted to, I would just, make it 0.9999, more nines here, or make it 1.0000, more zeros, and then the 1 there, to show you that it gets that close. All right. So the idea of arbitrarily close is if you have a certain idea, like Mr. Witt, I won't believe you until it's this close to -1. We could get that close if we needed to. Okay. We'll never actually get to the -1, but we'll get so close that we're going to say it's essentially -1. Okay. So that's a bit of a weird idea, right? Because in math, we're very close to like cut and dry, concrete, it's this or this kind of thing. But we're approaching here now instead. Okay, and so let me introduce then a definition. Okay, if f of x becomes, excuse me, arbitrarily close, and believe it or not, there's like a mathematical definition for arbitrarily close. We're not going to look at that, okay? And you won't even look at it in calculus, or at least in our calculus class. If you go on to take calculus in college, they may make that more of an emphasis, but anywho. If f of x becomes arbitrarily close to a single number L as x approaches a number C, oops, I don't know why I put a period there, sorry. From either side okay, then, so again, if f of x becomes arbitrarily close to a single number L as x approaches a number C from either side, that's the left side or right side, then the limit of f of x as x approaches C is L. Okay, lots of variables there. Okay, so I'll write it out here as a definition. The way we write that out symbolically is the limit as x approaches C of f of x equals L. Okay, that's how you would write that out. The limit as x approaches C of f of x is equal to L. All right. So there's like two different approaches that are happening here. One approach is x is approaching C. So C is some kind of like x value if you want to think about it. Okay, x is approaching C, and then as a result, the function, its value is changing as well as x gets closer to C. F of x is going to approach some number L if the limit exists, and stuff like that. Okay, questions on any of that? Okay, yes, Mabel.
Okay, but why is there a hole at x? Why is that the limit?
Okay. Oh, okay. So first of all, so those two questions you asked are kind of two different questions. So I'll answer the first one here first. Okay. So why is there a hole at x? At x equals 1, you're saying in this case.
Yeah.
Okay. So why is there a hole at x equals 1? Well, if you plug in 1 into the original function here, you get 0 in the numerator over 0 in the denominator. So it's kind of like an indeterminate form. Okay. So we have a discontinuity there. Okay. So does that help you at all? I guess.
But if it looks like it's supposed to be -1, then so is it just when the graph and the equation don't line up?
I want to say no. This graph is the exact graph of this function right here. It is the exact graph. So the idea, though, is that at 1, if you're going to be exactly at 1, there's a hole there. There's no value. Okay. But if we were to approach 1 from the left and from the right, then it looks like there should be a value in there to fill in that hole, so to speak. There should be a value, and it should be -1, right? And that's kind of the idea. So there isn't one there, but we can still approach it and still kind of get a value that we're approaching at least. But it's still not the value at 1. the value of this at 1 does not exist. Okay, because there's the hole there. Does that help clear it up a little bit?
Yeah.
All right, so, and if you have more questions, let me know. And so do you need any more? Is that good then? Okay. So, moving on. So as an example here of this, seeing this applied, so let me just use our previous example here. We can say the limit as x approaches 1, so I'll scoot that back up there. The limit as x approaches 1 of our function, 2x squared minus 5x plus 3 over x minus 1, that's got to equal what? What do we figure it out to be? Negative 1, right? Negative 1, right? The function, as x approaches 1, the function value is going to approach negative 1. Okay? So that's the idea behind that. Alrighty? So, yeah. Okay. So let's try another one here. So let's evaluate the limit as x approaches 0 of x over the square root of x plus 1 minus 1. And we're going to do that by completing a table. So first of all, we can see here, right, that at 0, there's going to be an issue, right? If we just try and just plug in 0, we're going to get 0 over what? 0 again. Yeah, because 0 plus 1 is 1. Square root of 1 will be 1. Minus 1 will give us 0. So it's 0 over 0 if you plug in 0. If you're trying to evaluate the function at that point. So let's make a table here. All right, so we'll make another table just like we did in the earlier example. Okay, I'm just going to use f of x. I'm just going to say this is equal to f of x here. Okay, just to make it easier. Okay, and so we'll approach 0. So I'll say like, I don't know, negative 0.1. We'll do like negative 0.01. And we'll do like negative 0.0001. Okay, because we're approaching 0 from the left there. And is that it? Or should I add more to our table here? Well, all right, we want to approach that number c from either side, okay? So we're approaching from the left-hand side here, from values less than 0. We also need to approach from values greater than 0. So like 0.001, 0.01, and I know this is like maybe overkill for some of you guys, but I just want to, show the full analysis here, okay? Just so you appreciate it. Okay. So you guys go ahead, fill that table in. You can use your calculators if you like. All right. Feel free to do it. In fact, I'd recommend you get your calculators out and just try to do it, so make sure you can, okay? Typing this into your calculator, that's half the battle, right? Maybe you can evaluate stuff, no problem, but typing that in accurately can cause some issues. Okay, in fact, so while you're, you guys guys work on that, and I'll get this filled in. Okay. Does anyone's graph look like that? Anyone's graph look like that? Good, it shouldn't. Shouldn't look like that. Okay? If it looks like that, that means you forgot to put parentheses around your denominator. Okay? So if it looks like that, you forgot to put parentheses in your denominator. Okay? Your graph should look like that. Okay? So good. I'm just going to fill in that table. Fill in that table there. Use calculator if you want to use that. Yeah, the table commands and stuff like that helps. Oh yeah, Jeff. Great question. Show you here. So, this is the insert command. So you press second. So where you want to put the parentheses between the division and the square root, right? So you want to highlight the thing after where you want the parentheses, or you want the parentheses before the thing. So you go right there. Second, delete. And now you see how the cursor has changed. And now if I press parentheses, it squeezes it in there. And you got yes. Yes, it should be too. Yes. You good? Good, right? Nicely done. Okay. Say one more time what do you mean by the negative?
So this
Oh, I see what you're saying. It's like it's not quite two. You see, there's still some error there, yeah. But your calculator can't give you that many decimals, yeah. Yeah, exactly. Okay, so I think you guys got the idea here. So there's what the table is going to look like, filled in, something like that. Okay. And so with this data at our command here, in our hands, I should say, we can then safely say, right, that the limit as x approaches 0 of x over the square root of x plus 1 minus 1 is what? 2. Okay. So there it is. Okay. The hardest thing here is going to be, for students I find, is coming up with these values right here that approach, especially when you have to deal with negatives. Okay, but also coming up with the right decimals that as they get closer. And over here on this right-hand side especially, because like it's weird, we start actually like here it makes more sense. We're progressively getting in closer to 0, but here we should start at the closest one and then get progressively further away to kind of see that kind of like converging behavior there. Okay, any questions on that? Right, good. Got a little bit more here I want to talk about then. So there are 3 approaches that we're going to be using to find a limit. Okay. Today we're going to we looked at one already. To finding a limit. Don't ask me why I capitalized the A there. No idea. Number 1, we're going to call the numeric approach. Okay. And the numeric approach is what we just did. Okay, it's the table of values. This is a legitimate method in some situations, okay? You won't always, you won't be able to necessarily have a graph sometimes. Sometimes you can't have a graph. Sometimes you also won't be able to do, well, anyway, you'll see. So this is something to keep in mind, right? I mean, it is a tool. Maybe it's not the most efficient way to do it, but it does work. Okay, tomorrow we'll look at the graphical approach. That's like looking at the graph to kind of like determine a limit. And then we're going to spend like a minute or two here talking about the analytic approach. And this is something that we're going to develop as we go throughout the rest of these couple of days, but we're going to start today with it too. Okay, and the analytic approach involves using either algebra to help us evaluate the limit, or sometimes we also use calculus. Now obviously we won't be using calculus, but later in calculus class, if you decide to take calculus after this, then you'll see how that works here too. You'll use a method called L'Hopital's method, and that involves using calculus to help you evaluate limits. Okay. Okay. One thing I want to note here, though, note 1 and 2 are methods of approximating. A limit. Okay. You might, I mean, and in a way, I mean, the limits that we found in the last two examples that we did, right? Those are the limits, right? But technically, we're using a table, using a graph. Those are approximations, but we can also, the two that we just did, we can back up with algebra too later and show that they are in fact what they say they are, what we think they are. Okay. So let me get into a quick overview of evaluating limits analytically. Okay, it's pretty straightforward what we're going to do today. Okay. In some cases, okay, a limit can be evaluated by using direct substitution. Okay, and this is where it can get a little funky, because it feels like when we do this direct substitution technique, it feels like we're evaluating the function. All right, it feels like a function evaluation, and it's very close to it, but it's not quite the same thing. Okay. So in other words, the limit as x approaches c of f of x is equal to f of c. And like Mr. Witt, that looks exactly like a function evaluation. And it's close to it, yes. Okay, but this is only true if and only if f is continuous. Okay, if your function is discontinuous, this might not hold. Okay, but if you know your function is continuous, and continuity in a very basic sense, right, is like if you can like trace out your function without having to pick up your pen, right? That's a continuous function. Then that works. And so I'll show you some examples here then of evaluating some limits. So evaluate the given limits. Okay. All right, so sorry, I'll slow down here. Okay, so we're gonna do 4 here together, and then I'll give you guys one to try. But they're pretty quick. All right, the first one, the limit as x approaches -4 of the function x. The limit as x approaches -4 of the function x. Okay, so is the function x, is it continuous? Yes, right? And so, what will this equal? -4. You direct substitute the -4 in for the x. Okay, they're continuous, so sub it in. Okay, number 2. The limit as x approaches 3 of x squared. 9. Yep. Just plug in the 3. 3 squared is 9. The limit's 9. The limit as x approaches 2 of the function 3. What will that equal? 3. Yeah, there's no place to direct substitute the 2 in. It's just 3, right? The function is always equal to 3, and so no matter what you approach, you're always going to be approaching. You're always going to go to 3. That's very boring. Maybe you think, Mr. Way, this whole thing's been boring. Well, sorry. That's like your opinion, man. All right, let's take a look at this one now. Rational function, x squared plus x minus 6 over x minus 2. Yeah, if we try direct substitution, what's the problem here? You get 0 over 0. Oh, no. But what can you do with that numerator? Yes, it factors. Okay, what does x squared plus x minus 6 factor to be? I really love using those, don't I? Anyway, sorry. What does it factor to be? X minus 2, x plus 3. Yeah, okay, very good. And then over the x minus 2. And those x minus 2's cancel. And then the limit as x approaches 2 then of x plus 3. So what's this limit? Careful, it's x is approaching positive 2, so 5. So the answer here is 5. Okay? You'll notice what's also missing here. I didn't write, so I said that this function here, this rational function, was equal to this rational function, right, where we factored, which was equal to this function, which was canceling out the x minus 2. But I said they were all equal. I didn't put the x not equal to 2 stuff that I had been putting earlier. Why? Because we are not at 2 ever. We are only approaching 2. And so this limit will be exactly equal to this limit, will be exactly equal to this limit. There's no need for me to stipulate x cannot equal 2 because x will never equal 2. We're only approaching the 2 here. And so I can then kind of like get around not plugging 2 in by factoring and canceling, and then now I can plug the 2 in for a direct substitution to evaluate the limit, and the limit's 5. Okay? So we are approaching 2. We never actually get there, yet we can still plug the 2 in to evaluate it because that's how we can evaluate a limit, right? Is by that direct substitution. So we can kind of like get around that indeterminate form there by factoring and canceling. So yeah, Ryan.
Do you have to write like limit and then x? Like,
Yes. Every step. Until you do the direct substitution, you got to write it out, or else it's not correct mathematics. And I will be a stickler for that. Okay? And it's not because I'm trying to be pedantic or anything like that, but like I'm trying to prepare you guys for calculus, and those of you that plan on taking it, right? I don't want that sloppy work because while I may know what you mean when you stop writing that limit as x approaches 2 kind of thing, an AP grader for the people that, again, that are going to be taking the AP test or taking the AP class or whatever kind of thing for, you know, next year or next, semester, I guess, whatever, anyway, same thing. They may not be, they might take points off because like, well, what's this mean? You went from a limit to just a function. What happened to the limit that you didn't evaluate yet? So you want to make sure that you're being, very careful with how you write things, okay? If you know that's you, if you're someone that kind of like is a little sloppy with their work and they get the answer, but the work doesn't always support it, your teachers, spoken to you in the past about it or something like that, that's something you want to fix before you move on to calculus, if you plan on going to calculus, because it's going to be important that, this random grader who doesn't know you from anybody else, they need to know what you're thinking. So you have to be able to, write it in correct mathematical fashion. Anyway, there's a limit for you to try, so go ahead and give that one a shot. All right, and then we'll be done after this. I'll get you guys started on your homework assignment. Okay, so what is the limit of this function? 2. Yeah, it's 2. We can rewrite this, right, as the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1. X minus 1's cancel, and the limits will still be the same. And so we get 2 when we do a direct substitution there for our final answer. Okie doke. Questions on any of that? All right, so your assignment is on the Google Classroom. I suggest you get started on it because this stuff is a little bit different, right? And so I'll come around and help you